Why don't we do a thought experiment first? So imagine you're going to a Michelin three-star restaurant right now. As you walk past through the door, you notice there's a bunch of happy customers there already, right? You find a seat, sit down, look down at your menu, pick the couple interesting things you want to try. Then the waitress comes over, take your order, right? Now you're kind of stuck with that eagerness of waiting for that hot sizzling food, at least for a while. So let's use the time to imagine what's happening in the kitchen. So the kitchen may look something like this. It's pretty clean, it's well organized. The head chef is running the show, but the line cooks are actually manning their own stations. They all tend to have their own responsibilities. The communication style is very concise and effective. So all this collaboration, orchestration, and workflow just make it look so easy for a well-managed kitchen like this to pump out that few hundred items every single night at peak hours. So how do they do it? So I recently read this book called Kitchen Confidential by Anthony Bourdain. The book is great. I mean, it revealed a lot of secrets in the kitchen, but what's important for me is actually made me realize there's a whole lot of similarities between running a distributed system and running a kitchen. So I can share a couple examples here. In Netflix, we do have hundreds of microservices that work together to achieve one single goal, which is to provide the best online video streaming experience for them. But when you look down at each individual microservice level, they all tend to have one single responsibility, and just one, and does it really well. This is very similar to the line cook. There's nothing really innovative about what they do. The real job for them is all about that mindless repetition to get that one ingredient right to perfection before passing to next line chef, right? So this is very similar. Let's also talk about communication patterns. So you might have noticed in the kitchen when the head chef communicates to the line cook, you tend to hear a lot of declarative statements like, can you prepare me 2 well-baked potatoes with skin removed? On the contrary, you will rarely hear statements like imperative statements like, go ahead, wash 2 potatoes for me, bake them for 10 minutes, and peel the skin for me, and do it right now, right? So there are details. I mean, all these little details, there are reasons behind them. So today, why don't we explore some of these details together, in our system? So today's topic is running a massively parallel, self-serve distributed data system at scale. We're going to be covering what is this real-time infrastructure we're building at Netflix, and why do we build it? And the title kind of infers there are 2 major challenges we have faced. The massive parallel indicates a scale. The self-serve distributed data system kind of infers it's a multi-tenant system. It's self-serving. So there's a lot of issues we run into when coping with changing environments and need to be resilient to failures. So we're also going to be talking about those. Let's jump right in. So what is this real-time data infrastructure we're building at Netflix? So with over 100 million subscribers worldwide, and almost any internet-connected screens are now capable of playing Netflix, there's actually the entire ecosystem is generating really a lot of events that we can leverage at the backend, right? So things like when you click on the play button, you click on the pause button, or you just simply browse through the video catalog. So all of this user action get translated into events that we collect at the backend. And some of the microservices we mentioned, I mean, they just leverage this data to help with improving customer experience. For example, doing better recommendation and personalization algorithms. And since you might not be well off is some of the content operation, they also use data to make better content purchase decisions so our users can get better content. The list goes on. I'm not going to go too much details into it. But on the other side, on the architecture side, you might have here, with the recent rise of event-driven architecture, you might have here patterns like notification pattern, event sourcing pattern, CQRS, which stands for command query responsibility segregation pattern. So all of this pattern here is becoming more and more popular, especially in a microservice environments, right? So if you look at the commonality between all these different patterns, it all requires events to be collected, persisted, delivered, and processed, right? So by having a common infrastructure platform, we can allow our microservices teams to be able to innovate better. So with some of the event-driven patterns we just talked about and some of the traditional stream processing, It's typically implemented on top of an enterprise application integration or enterprise messaging bus solutions. So it's proven these solutions are quite real-time. But also on the other side, I mean, because of the design limitations, it's proven not to be very scalable, at least not to our needs. On the other side, the good old batch processing system the industry has been using for the past 10 plus years, it's reliable. I mean, it's scalable, it's proven. But it's well known this type of job gets very long. The turnaround time for them is very long, especially given today's increasing amount of data. And Netflix, some of our jobs runs over a day, 30-something hours, which is becoming unacceptable. So here is where we come in. We want to build this infrastructure, the streaming platform that's both scalable and real-time. By now, you guys probably have heard a lot of data-driven culture in Netflix, so I'm not going to repeat the obvious over there, but I do want to splash some more color into it. So by having this distributed microservices architecture in Netflix, a lot of the teams tend to have more than one microservices. They manage that or operationalize those, right? So they tend to make a lot of local decisions. They don't want to having to consult a centralized decision-making process. So we do want to build this platform to also support them to make those local decisions as well by giving them the capability to consume data, any data they want, across different organizations, across different business units, or even across different technology barriers, right? So that's allow them to consume the data, but we also want to allow them to write their own logic to process the data at real time whenever they want. So what exactly is this Keystone streaming platform? We help publish, collect, move, and compute event data in near real time at cloud scale. So Keystone is also a collection of microservices and components. We internally break them down into the control plane and data plane. So the control plane is responsible for doing all the management and orchestration. So kind of sort of like the head chef, right? The data plane does the heavy lifting and making sure things happen. So it's similar to the line cooks. Although we have a bunch of internal microservices, the entire Keystone infrastructure appears like a single self-contained logical platform as a service to our user, so they don't have to know about all the details. Keystone is a multi-tenant self-serving tool. Keystone is self-healing, cloud failure tolerant. It guarantees at least once delivery, and it's capable of adapt to changing environments. So putting everything we just talked about together, this is a very high-level architecture of ours. We mainly have two major product offerings. The box in the middle left, which is our internal event routing infrastructure that's responsible for routing every single event in Netflix into both batch systems and real-time streaming infrastructure. So the box on the right is our stream processing platform that allows our user to program against specific underlying stream processing engines. Currently, we do support Spark Streaming, Apache Flink, and we internally have this custom stream processing engine called Mantis. So we allow users to program against each one of them, and we allow them to use this common infrastructure to deploy and operationalize the stream processing jobs. So one question you might have here is, why do we need to have that secondary Kafka cluster to support the streaming use cases, right? And there are two major reasons behind that. One is we don't want any arbitrary consumers to be attached to the front-end Kafka cluster, so we can protect it in case things fails and we need to do operations on it, the customer won't be affected by it. The second scenario is we do want to provide that kind of abstraction to our users. So when we internally, for example, having to scale topic, increase partitions, or do some things to do some mitigations in our platform, we can provide a kind of abstraction layer to our customers as well. So let's jump into the challenges and our solutions. The first one is scale. So for any scalable and reliable system, it normally starts from somewhere much smaller, right? So let's talk about a single stream, which is a very basic unit of deployment for us. So if you get one single stream right, you can probably scale better on a higher level architecture. So this screenshot is taken from our self-service UI that does the router infrastructure, the routing infrastructure, which a couple of slides earlier, which is the middle box over here. So when the user comes over to this UI here, they are able to configure a topic they can wire up their producers to write into. They can optionally define some sort of a custom transformation through our high-level DSL. So currently we support two major DSLs. One is filtering, and filter is supported by XPath syntax. And we also support projection, which we currently support both blacklist and whitelist projection on certain user-specified fields. In the future, we're also looking into supporting JavaScript DSL and SQL DSLs, and those will be integrated into the UI as well. So finally, the user can configure sync. They can have all the payloads to write into. So this is all from the user's perspective, what a single stream looks like, right? So there's an important concept I want to bring up front. So for stream processing job, there are two major stream processing paradigms. One is called massively parallel, or another term for it is actually called embarrassingly parallel. So that just means the workload itself can be easily parallelized. The routing infrastructure is actually a perfect example for that. So every single partition can be processed independent of each other and can be just run in very parallel fashion there. The second paradigm is the more complex MapReduce style of stream processing job, which typically involves sorting or shuffling over the network. It's a completely different beast to handle. It typically involves managing large local states, special handling on chip pointings, doing a lot of optimizations on data locality when computing data. So today we're going to be focusing on the first paradigm, which is the massive parallel. So unless otherwise specified, I want you guys to assume we're talking about the first case there. So after taking a look from the user's perspective, let's take a look at a single string, autonomy of a single string from the components field, right? So when the event producer produces events into our queuing service, which is built on top of Kafka, the stream processing job, we currently built the router on top of Apache Flink. It is responsible for consuming all the event payloads from Kafka cluster, performing all those transformations the customer defined, and eventually write to the sink. So this is just happy path. If normal case, it would just work, right? So let's also talk about some of the customer expectation on the different scenarios. Let's first talk about scaling. When we initially bring up the string for the customer, we do ask them for some initial input on how big the topic might be, the traffic volume for it. And the reason why we need that is we need that to perform the initial provisioning and deployment. But as time goes by, the topic can actually spike in traffic or decrease in value, in data volume. So when that happens, the customer typically expect the entire platform will automatically scale to cope with the load. So handling failures, there are different types of failure scenarios. For example, on the instance failure, when EC2 instance is gone or the container is gone, customer typically expect the entire platform is self-healing and it recovers within seconds or minutes. On a larger infrastructure failure, the customer still expects the string to be delivered in at least once delivered semantics. We're going to talk slightly more into that. So that also means the stream processing job is responsible for maintaining its own state by performing checkpoints and doing offset management. So this is a slightly more dived-in view for the two major components we have. So for those of you who are not familiar with Kafka or Flink, I'm going to briefly talk about them here. When the event producer produces events into the Kafka cluster, Kafka provides this sharding mechanisms to allow events to be load balanced into different partitions. And each partition is essentially just a commit log that associates each event with the offset. So on the right side, a Flink cluster is comprised of a job manager, which does the coordination or orchestration, and also actually performs leader election through Zookeeper. So the task manager is actually the one that does the heavy lifting. Each task manager can run one or more parallel tasks. Each parallel task for the massively parallel cases normally implements like a source operator, a map function, typically does a transformation, and a sync operator that writes out to the sink. So because the nature of the massively parallel case, it's Flink internally can chain this operator together and allow them to be performed inside a single parallel task. So each parallel task, each source operator is responsible for consuming from one or more partitions. The exact mapping depends on your workload. So if you have a more CPU-intensive workload, you might want each task to consume from less amount of partitions. So as you guys can see here, the Kafka cluster, the sharding semantics, and the parallelism defined on the Flink job cluster is completely separate, independent of each other, that allow us to scale both systems independently. So another common thing that the stream processing infrastructure need to handle is the back pressure. So when there's network partition or slowdown in network or the actual sync has problem with it, and also if you want to guarantee at least once delivery semantics, what needs to be happening is you want to keep retrying that record until it's successful before you commit in the offset, right? So when this happens, when it continues to fail, the back pressure will be accumulated and propagate all the way from the sink to the streaming job, and eventually will cause loads on the Kafka cluster. If Kafka cluster is under too much load, eventually this back pressure will be propagated to the producer. This is what we want. And of course, we don't want to get into the situation where the payload is getting lost. But this is a long process. It typically allows us time to perform monitoring and alerting on this and perform mitigation steps on it. So briefly just talk about separation of concern. So we do want to separate the messaging layer, the Kafka layer, and the stream processing layer. So they can scale independently, they can manage their own states, they can independently manage their own dependencies. For example, Kafka brokers are deployed on top of EC2. But for stream processing jobs, it's more of a natural fit to run those on containers. So it allows us to quickly spin up jobs and tear down jobs more effectively. So container runtime, we internally have one team to manage this container runtime infrastructure. It's called Titus. It provides a lot of the feature we actually leverage. For example, resource provisionings, scheduling and bin packing, capacity guarantees, resource isolation. I want to mention this one last bit here, the per container IP address through AWS VPN underlay. Right? So it is a very useful feature for us because when you have each container can have its own IP address. It allows us to not worry about certain things like internal service discovery through port mapping. So it makes things a little bit easy for us. And also this Titus container runtime is the immutable infrastructure for us. If a container goes away, they guarantee the container will come back. It might have a different IP address, it might have different characteristics, but our internal on the application layer will be able to rediscover that container and redispatch the job to it. So let's get into delivery processing semantics. There are three different processing semantics here. At most once, at least once, and exactly once. At most once is the most easy to do. That means if you can't handle it, just drop the payloads on the ground. There's really no guarantees there at all. So we're going to be focusing on the at least once and exactly once guarantee. There are typically two major ways of ensuring at least once processing semantics in a stream processing job. One is called synchronous checkpointing through event loop. So I know this event loop term is overloaded, but just bear with me, try to explain here. So when an event reaches a processing thread, we want to perform the process method, window method, and checkpoint method synchronously and sequentially. And when either one of these fails, we want to keep retrying them until it succeeds. Before, the most important part is that checkpointing, or which commits the offsets, right? Now, there are slight variations of this implementation that allow some certain type of user workloads, like IO-intensive workload, to be parallelized inside the processing methods or the window methods. The main idea is still the same. It's just, breaking those process into little batches, and the checkpoint is still guaranteed to perform on those little batches. The second approach is called lightweight asynchronous snapshot or async barrier checkpointing. This is a very good paper published for this. I would encourage you guys to actually read into it to understand a little bit more, but I can give you a very high-level view here. For a massively parallel case, the source operator will emit barriers that travels along with all the payloads. So when the barrier travels through the entire processing DAG, when it finally reaches this, the sync operator, that's where the sync operator actually does a commit, take a snapshot and does a commit. Now I want to mention there's a difference between exactly once processing semantics versus delivery semantics. So the processing you can achieve exactly once processing semantics as long as you can guarantee by processing one event, the side effect of processing this one event typically results in some local state changes, right? As long as you can guarantee this local state change is exactly the same as you just processed this message once. It doesn't matter how many times you process it, as long as you can guarantee that, you have achieved exactly once processing semantics. However, if you need to deliver the events into some external sinks where the barrier cannot be reached, or if the sink cannot support idempotent operations, essentially you really cannot guarantee exactly once delivery over there. So it kind of reverts back to at least the once delivery semantics. So finally, I'll just share some example of our signals that we use for doing monitorings and loadings. We cannot go through each one of this. I just take one example here. It's a very important metric I think you guys need to think about. It's called consumer lag. So we actually have an external service that monitors this consumer lag. And the way we monitor is we look at the last checkpoint offsets and compare these offsets with the Kafka loghead. This is the difference, right? So we use this difference to compute the actual amount of time we need to catch up. This becomes an indication of how much time, how much time you have lagged behind. There are some other alternative approach for doing this. For example, you can directly monitor Kafka consumer lag metric, but I would recommend against that. The reason behind that is we can get very philosophical about it. Distributed system is like human. They lie sometimes. So in this particular case, we have noticed in some failure scenarios, the Kafka metric will just not showing up, right? So when you don't have the consumer lag metric, it's not like you don't have a lag, it's just because you can't observe it. So you want to have some external service to be able to monitor those. So that was just all about a single stream. Let's look at a slightly complex scenario over here with fanouts. So this is one of the popular streams we have, topic we have in Netflix. It has a fan-out factor of more than 10. And because we support different delivery sinks and support different transformation logic, so people will actually take advantage of that. We do support batch system, which typically delivers within minutes, and the stream processing system is normally delivered within seconds. So with that kind of fan-out, there are failure cases like when a particular sink is bad, or there's network failures. We want to protect other streams against the failure like this, right? So when a single stream fails, we don't want other streams to fail. So we need to have some sort of isolation between streams as well. So the way we do it is deploy every single string into a single Flink cluster. As I mentioned before, each Flink cluster is comprised of a job manager and task managers. The job manager overhead is actually not that big. We run job manager instance using a single CPU and 250 megabits per second network, and that's more than enough for doing massive parallel coordinations like this. So when we do that, you kind of guarantee strings are isolated from each other, but there are shared services like zookeepers and S3 state backends. There are points you want to guarantee, you want to have isolations and separations on those paths as well. So those are the co-paths you need to worry about. So another point here is this allows string to be isolated from each other. This also allows when you do a red-black deployment, for example, when you bring up the new cluster, you also want to have that isolation there. One case we have observed before is if you don't have that kind of isolation across deployment, the new cluster you brought up might actually join the old cluster. So the workload, it's a little bit more challenging to balance the workload as you bring up a new cluster and tear down old clusters. So going back to this fan-out graph over here, as I mentioned, this is a very popular topic in Netflix, we have observed during peak hours the incoming byte rate reaches over 4 gigabytes per second. With this sort of fan out, the fan out traffic is more than 20 gigabytes per second, right? So I don't know about you guys, but we recommend against building very large Kafka clusters. We typically recommend building no more than 100 or 200 brokers, especially running in the cloud, because there are very interesting failure scenarios happens in the cloud. So when you have a cluster like that size, supporting a topic like this becomes a challenge, right? How do we solve it? We actually use hierarchies to solve this problem. Sometimes when the fan-out factor becomes too big, we can route the stream into a secondary Kafka cluster and allow the fan-out to be happening on those secondary Kafka clusters. So that was just a single topic. Now let's talk about our total infrastructure scale. We collect more than 500 billion events. It's generated every single day. We process more than 1 trillion messages every single day. We have more than 800 topics. So imagine that one fan-out topic, we have like 800 of them. We have 18,000 streams. We have 4,000 plus Kafka instances and more than 9,000 stream processing containers today. So with that kind of scale, it's natural to conclude that you're gonna need more than one Kafka cluster, right? So I strategically placed that block over there, so security won't yell at me, but you guys can still kind of figure out we name our Kafka clusters after mountain range names. They all have different sizes, they have different guarantees, replication factors, stuff like that. But there's one thing I can guarantee you, when you have tens of clusters inside a single region, and we have 3 regions, right? So we have more than 30, 40 clusters we manage worldwide. When you have a cluster size like that, there's only one thing that's guaranteed. At some point of time, you're gonna have the Kafka cluster will fail at some point of time. So we do design and prepare for those type of situations. So when that happens, we spin up a failover cluster, rewire the producer traffic into the failover cluster, and rewire the router to consume from both old cluster and new cluster. And the reason why we still want to consume from the old cluster is even if it's in a bad state, we still want to drain those messages out to try to reach that at least once delivery guarantee. So next step, we go back to the old cluster. You know, if it's recoverable, we try to recover. If it's unrecoverable, we repave the entire cluster, try to resurrect it. When everything goes back fine, we move all the traffic back and decommission that failover cluster. This is the current approach we take. So that brings me to bring up this interesting concept here. So just quick show of hand. How many of you guys have heard of pie versus kettle? Okay, cool, awesome, a lot of people. So it's essentially just an analogy that's comparing different deployment models in data centers versus in the cloud. In the old data center traditional way, when there's a failure happens on an instance, the ops people will go in, right? If there's a disk failure, swap out the disk. If it's a network card, swap out the network card. So the machine was repaired in place, and the software instance was redeployed on the same instance there. So it's kind of like a pet, right? You nurture back to health. So in the cloud environment, if an instance goes bad, they don't bother with that. They just swap out an identical instance type and deploy the same software instance on top of it. And when you write the software, when you write the software architecture, you expect it to handle this type of failures. It's very normal in the cloud, right? So if you guys remember a couple slides ago, we have those mountain range names for the Kafka cluster. They're all different in size, right? Some people on our team need to have special knowledge about those clusters in order to perform mitigations. Typically there's a runbook somewhere recording this information, right? That's not ideal for us. So can we do immutable infrastructure on Kafka clusters? So this is currently an initiative we're trying to do to allow us to do that immutable infrastructure on the Kafka cluster level. Since we can leverage from it, for example, when Kafka failover happens, right now we have to fail back, right? In the future, we just have to keep failing over. There's no third step to fail back. And when you want to scale up your topic by adding partitions, in some cases you want to lower the amount of your partitions. I know currently this is a very challenging thing to do, right? But when you have an immutable Kafka cluster, you don't have to shrink the partitions. You just create a new topic on a new Kafka cluster, and that's it. It becomes immutable. So unfortunately, we don't have enough time to drill too much details into this. But fortunately, one of my colleagues, Alan Wang, he recently gave a talk on Kafka Summit. So I include a link to that talk. So if you guys are interested, you guys can explore a little bit more into that. So just quick recap on the principles we just talked about. Failure as a first-class citizen, separation of concerns, and embrace that immutability. Let's jump into the second one. So what problem can you run into when you have a self-serve and multi-tenant system? So first of all, they all have diverse requirements. They want to use different combinations of your features, right? And just expect it to work. And sometimes they have diverse platform trade-offs. For example, when things fail, sometimes they prefer latency over duplicates, and sometimes vice versa. So we need to handle that. And when you have multi-tenant system, the change is only constant. What are the changes? So when a new string is, they expect the deployment happens within minutes, and customer keeps changing their requirements. They will go in there and change their DSM, doing experiments in production, right? We kind of support them doing that. They expect those changes will be deployed within minutes as well. So there are certain scaling activities, like increasing traffic that we need to scale the infrastructure. There's also infrastructure upgrades all the way from EC2 upgrades to container runtime upgrades to our stream processing engine version upgrades or Kafka cluster upgrades. So all of those are constant changes, not just coming from the customer and also from the infrastructure. So there are changes from all directions. So that sounds hard enough already, right? So we also have this failure modes. The infrastructure can fail at any point of time. You can have instance level failures. You can have availability zone completely wiped out in a availability zone. And you can have regions be unavailable for some period of time. That doesn't happen very often, but it does happen sometimes, right? So we design for those as well. And also when you're in a microservices environment, you always want to assume other components can fail or become unavailable at any point of time as well. So you want to design for those. So to solve the diverse requirements problem, we build every single feature we have as building blocks. So customer can just pick and choose and just satisfy their requirements. The way we do it, just take a couple examples here. So for example, all the connectors we have, the source operator, the sync operator, and the transformation logic, we basically write those into separate building blocks, so customer just pick and choose. And to solve the constant change problem, I want to introduce this idea about declarative reconciliation. So this allows us to scale better in face of changing environments and constant failures from all the directions. Not just scale architecturally, but also allows us to scale operationally as well. So my team only has 10, 11 people on it. And managing infrastructure like this size, we don't have a lot of luxury to do a lot of things manually. So we have to build those designs into the architecture to allow the architecture to be able to reconcile eventually to converge into customer requirements. So before diving into the details, I want to give you guys a challenge to think about. So why in the kitchen, the orders are immutable? That means when a customer changes the order, right, they don't typically modify in place, but instead they add slips at back, right? Keep appending to it, it becomes immutable. So why is that? Think about it. So let's talk about declarative reconciliation. So declarative is a communication pattern that allows authority to assign goal states to sub-level components. Reconciliation is to allow those sub-level components to drive its internal states to eventually converge into that goal state. So we just talked about the goal states, and for each sub-level component, each one of them need to have this capability to discover its current state by looking into the underlying infrastructure. We'll talk more into that, but let's take a look at a concrete example here. When the user comes into our UI to define their requirement, that's essentially the goal state for our management layer, which is the control plane. There are certain things the customer cares about, for example, the topic, the transformation logic, the actual sync. There are certain things the customer don't care about at all, like, for example, how many partitions we have, where this particular topic resides on which cluster. So those, we can relay those decisions to individual components to allow them to make scenario-based decisions. So when this happens, the goal states flow from the control plane to the data plane. And each component in the data plane leverages reconciliation to discover its current state and eventually use a technique to drive towards goal state. How does it do that? So it's natural to think of a state machine at this point. So this is an example of our deployment engine that allows customers to specify whether they prefer low latency or low duplicates during failure scenarios or during deployments. And basically for the stream processing infrastructure, the component, you can discover its current state and look at the goal state, compare the difference. And that allows you to land on a particular state over here. And with the state machine, as long as you're making forward progress, it's automatically tolerated to failure. You're eventually going to reach that goal state. So let's talk about failure scenarios. One interesting thing we have run into before is, actually a quick show of hands. How many of you guys rely on Zookeeper as the source of truth for your Kafka cluster? Okay. What we found out is it's not reliable. It will fail. I'm telling you, it will fail at some point in time as well, especially when you run into the cloud. One issue we have observed before is due to some sort of a weird network partitioning issue, the Kafka controller can get out of sync with its own brokers. So the metadata information returned by the broker, like a regular broker versus controller, is different. That causes problem. Sometimes it's unrecoverable. There are one other case where we notice like really heightened long GC time happens for more than 10 seconds, 20 seconds, which resulted in Zookeeper session timeout and eventually resulted in this cluster being unrecoverable as well. And the real reason behind that long GC pass is because the GC operation is actually trying to write out that GC log, which is actually on the GC path. It's competing with some other, on Kafka broker, right? So it's IO intensive. It's actually trying to compete with that particular IO in the kernel. It doesn't happen very often, but when it happens, you get into that situation, it becomes unavailable. So is this architecture allows you to be resilient to that? I'm saying yes, because even if you wipe out the entire Kafka cluster, that's okay. You can rely on that reconciliation, that single source of truth coming from the control plane to allow the reconciliation to happen. As long as you can recreate a different Kafka cluster with the same topic, you can eventually recover from this situation here. What about the container runtime goes down? What if the container runtime cannot take any, it becomes unavailable for some period of time? As long as you have existing containers still running and performing its job, we have this constant reconciliation and will allow us eventually to be able to submit those new jobs into this container runtime. So it may become unavailable for some time, but it's eventually consistent. It allows you to do that eventual convergence on the goal state. What about the control plane goes down? That's also okay because you still have the data plane running at that point of time. They're just not getting new instructions. They're not able to deploy new streams. But as soon as the control plane comes back, we can continue to allow customers to interact with the UI. So this allows, the single source of truth allows eventual convergence on goal states. So quickly recap over here as well. Some of the principles: leverage reusable building blocks, leverage declarative reconciliation, and single source of truth. So going back to that challenge I gave you guys earlier, so why that is immutable. I think from my perspective, I think human beings are inherently not very good at computing diff on two documents. So in order to mitigate that, human beings can append information at the back of the statement document, so allows them to actually perform that diff very efficiently, very quickly. So this happens in the kitchen, allows human reconciliation to happen, right? So some more thought experiment for you guys. If you guys think of more principles that we can leverage from kitchen management versus distributed system, definitely let me know. I would love to discuss that. So that's it. I've included a couple references over there, and we're hiring. So contact me if you're interested. And also, if you have any questions, feel free to tweet me. I would love to interact with you on tweet as well. Cool. I think we have a couple minutes for questions. Okay, 2 minutes. Any questions? All right, I'll be here. So if you guys have any questions, feel free to look me up.